In this video, we're going to start to investigate how derivatives and differential calculus work in multivariate environments. When we looked at single variable calculus, we would talk about a derivative as df dx, or the rate of change of the expression in the numerator, f, with respect to the x in the denominator. When we look at a function of x and y, then what we're going to be looking at is the rate of change of our function f in terms of x first. Well, what do we do about the y? Well, we were going to treat y as a constant, so we're going to describe the rate of change with respect to x when we change x only. And we're going to have to ask a second question, which is how does our function change when we change y only? This leads to two different potential derivative calculations, or two possible derivative values. And the way we encapsulate that or reflect that in our terminology is that each of the derivatives only describes part of the slope information. And so these derivatives that we're going to be looking at are called partial derivatives. If we look at a graph of z equals a function of x and y, again, this would be a surface if we're trying to imagine it geometrically. The partial derivatives will tell us how the height of the graph, z, changes at some point, and if we move in a certain direction relative to that. So imagine we're at a point x naught, y naught, and there's a surface defined from there. If we're considering the x derivative of z with respect to x, and x is going out in this direction, then what we're going to do is take a step in the x direction. So we start at x naught, and we go to x naught plus a little amount, here called h, but sometimes called delta x. And we're going to see what that reflects itself as in terms of change in height. So we're going to have a change in height and a change in x. If we take that ratio, that's going to give us a slope. And if we take that h and let it get smaller and smaller and smaller, or take that delta x and let it get smaller and smaller and smaller, we're going to have a derivative in that direction, in the positive x direction. We can do exactly the same thing in the y direction. Imagine our surface goes on for a little bit further here. If we measured the rate of change, or the distance we've moved in y, and the change in z as a result, we can talk about the slope connecting that rise and run, and that would give us the rate of change of z in the y direction. As you can see, we're going to be talking much more specifically about the elements in a derivative, the rate of change of what with respect to what, because we're going to need to be more explicit than we sometimes got away with in the past. The notation for partial derivatives is similar to regular derivatives, with a minor tweak to the symbols that we use. Where we use d's in the regular single variable derivatives, we use this curvy d, or what's called the die operator. And it sounds very malevolent, but it's not. This would be phrased as die f, die x. This would be phrased as die f, die y. And we use those when there's an indication that there's more than one derivative that we could take. F is a function of two variables, x and y. We can take a derivative with respect to x, and we can take a derivative with respect to y, and those are going to be separate operations. So we represent those derivatives as partial derivatives using this curvy d, or die notation. What does this actually represent? Well, in terms of the limit definition, going back to our picture here, if we're taking the derivative with respect to x, the partial derivative with respect to x, we're going to have a small change in x, but the y value remains constant. And so you can see that in our formula here. Here we have a change in f over a change in, looking carefully at the expression here, there's only one value changing from this side to this side. So it's a delta f over a delta x, but with a limit as the delta x approaches 0. So it's approximated by this difference here, but if we want the actual derivative, we take the limit as that step size goes to 0. And another notation we use this for short form is f sub x, x naught, y naught. In the y expression, everything else is the same. Notice it's important here to distinguish what's on what side of the comma. When we talk about the change in f here, we have the same x value used, but what differs in the y derivative is the position in y. Here we take y naught as our base point, and we compare it to a point that's a little bit further along in y, going out in the y direction. We go out in that a small step, figure out what our change in f or change in z is, and we approximate that then as delta f, delta y, which will be a separate calculation than it was for the x direction. Again, we can write that in a more compact form if it's easier as f sub y at some point. What we're not going to be able to do anymore is use primes, because the prime notation assumed that we were taking the derivative of the variable that was the input. Here we have two input possibilities, so we're not going to be able to talk about f primes from this element on, or from this day on in the course. We're going to be focusing on more explicit derivatives, f with respect to x, f with respect to y, or some other input and output relationship. Now, how do we do the actual calculations? It seems at first glance like it might be a horrible process, but it turns out to be quite straightforward. The idea, again looking at the definition of these derivatives, is that we are going to change x if we are taking the partial of f with respect to x. We keep y as a constant. So literally, that's what we're going to do as we take the derivatives. We're going to imagine that y is fixed, and that for the purposes of the derivative, we only have a function of one variable. If we're doing the derivative with respect to y, we're going to imagine that x is fixed and y is the variable of interest. So as we do the partial derivatives, we only have to worry about one variable being a variable at a time. Let's see this in action. Here's a reasonably complicated function of x and y. What we're going to do is make this a new function, g of just x, one variable. And what we're going to do to achieve that is just fix or make constant that y value. All right, well, if we do that, our g of x is going to be x squared times y naught plus sine of x times y naught. And so again, what we're imagining now is that these two y naughts are constant. Well, once we've done that, taking the derivative of g with respect to x, using the regular d's for this scenario because x is the only variable left, well, we just go down the line and say, well, we have x squared times a constant. The derivative of that is 2x times y naught. And the derivative of sine, something with an x in it, would be cos. And we keep the inside the same. And then we multiply by the derivative of the inside with respect to x, and that will give us 1 times y naught. And if we tidy that up, we'll have 2x y naughts plus y naught cos of x times y naught. So this calculation, this derivative calculation, is the same as you would have done before. The only element that might be a little different is the number of constants that are represented as letters here compared to just number values. Note that this derivative here actually reflects the rate of change of f with respect to x. We can actually convert this back and talk about f sub x, or the x derivative, the partial derivative of f with respect to x, is equal to 2x, and now we just replace all the y naughts with y's. Well, that's an interesting process if you think about it for a moment, because all we did was rewrite the y values in the original formula with y naughts, and then just treated them as constants and then converted back to y's. That's a bit of overkill, actually. If we just reasoned with this and just thought of or looked at the y's as if they were constants when we did this, we would have ended up exactly the same place without all this intermediary work. Let's see if that actually works in practice for the same function. If we're going to take the partial derivative of f with respect to x, we pretend that x is our variable for this calculation. It's actually not pretending. X is the variable when we're taking an x derivative. And when we do that, we treat y as if it were a constant at every step. So we just look at this y here and pretend it's a constant, because it is not changing when x is changing. So we'll have 2x's times the constant y. Then the derivative of sine times something is going to be cos of the same thing. And then times the derivative of the inside with respect to x. I'll actually do this explicitly here, though with some practice we skip over the step. We take the x derivative of x times y. Copying everything we have already down, we can then focus on this term, and the x derivative of x times a constant is just the constant. And notice that that gives us the same formula we had on the last page without the intermediary step of sticking in y naughts. For the y side, what we do is exactly the same process intellectually. It's just what we treat as a constant and what we treat as a variable. So I'm going to write down the formula here so we can reference it and highlight the y terms this time. The x's are constant, and so too is x squared. And the y's are the only terms that are variables. We're taking the f derivative with respect to y, and so y is the variable, y is the variable. All right. Imagine this then like 3 squared. What's the derivative of 3 squared times y if we're taking the y derivative? Well, it would be 3 squared again, or here, just the x squared, times 1 for the derivative of y. The derivative of sine with a y in it is going to be cos of the same thing. And using the same logic as before, we take the y derivative of the inside, x is a constant, times the derivative of y is 1. We're going to have times x. This may seem a little alien at first, and it is similar to what you would have seen before with, or it looks at first glance like it might be similar to what you saw with implicit differentiation. But the key thing that separates this or distinguishes this is that x and y are unrelated variables in this scenario. Explicitly, x and y can go in different directions, have different values. You can pick x and y in any way you like. That's what makes this a function of two variables. So what we're doing here has similar symbols to things that we've seen before, but it's a very different interpretation because the meaning and the relationship in x and y here is quite different. We can change x and keep y constant, or we can change y and keep x constant and talk about the rates of change in those two directions as totally separate entities. Now, with all that theory, the best opportunity here is simply to practice. Do a lot of differentiation like you would have done in single variables just to hone your skills again, and practice this new ingredient, this new element, this new wrinkle that when you take the derivative with respect to one variable, you treat the other variable as a constant. And you can switch back and forth when you take the derivative of the second variable. We will see some more practice as we go through the following videos.